Okay, let's get it. Let's go. This is Wednesday, my dudes. I'm just gonna do a major PowerPoint extravaganza. Let's do problem one from every PowerPoint. And then so on and so such. I'm gonna star this. Do want to come back to that before the night is through. No boy, no. Let's start with the nonsense. Chapter 21. Boy, they literally could not make PowerPoint on the browser slower if they tried. What's Coulomb's law? Here we go. I'm gonna try to not peep the answers. Okay, I got it. I didn't see. These slides can get so messy though. Big enough so I can see. Okay. We've got Q1, Q2, and Q3. And Coulomb's law is, well, it's actually, let me open up on Google Docs a formula sheet that I might use. I'm still not sure if I'm going to use it or make my own, but it was offered to me, so might as well try it. Formula sheet's a bit messy. Can I save it as a PDF and then just see it as a look at it as a PDF? It's just one page, but PDF's cleaner to look at. I can also hit like F11. Okay. So formula sheet says F12 equals K Q1 Q2 all over R squared I hat. That's dead on the exact formula, but we want to know the electrostatic forces on Q2. So we can do Q21 and 32. Oh no. Well, that's later. That's and we have 1, 2. Yeah. So we know that Q1 is 3 microcoulomb. Q2 is -4 microcoulomb, and 4 is -7 microcoulomb. So all of these now become 3 times 10 to the -6 coulomb. And figure of speech that they all become 3. -4 times 10. -7 times 10 to the -6 coulomb. Okay. And And we're gonna have different R's. I guess R 1, 2 is 0.2 meters, and then R 2, 3 is 0.15 meters. So what this means is we're gonna have an F12, and we're gonna have an F23, positive to negative, positive to negative. Yeah, that is about where I'm going. It's already in the darn thing. It's like giving me a hint. I don't want one, but it's what else. So this is going to equal 8.85 times 10 to the negative 12. And both of them are going to start with this. Little sheet here. Calls it epsilon. This is 8.99 times 10 to the 9th. Epsilon 0 is the 8.85. That is my mistake. So with that, this is going to be times. Oh boy, we actually might need to make that a little bit larger. I just made it the same size. Q1, Q2, 3 times 10 to the negative 6 times what would be just 4, because absolute value of 4 times 10 to the negative 6 over 0.2 squared. And then this one would be 4 times 10 to the negative 6 times 3 times 7 times 10 to the negative 6.15 squared. Oh my gosh, my calculator. Here it is. I'm getting 8.99 times 10 to the 9th times 3 times 10 to the negative 6 times 4 times 10 to the negative 6 all over 0.2 squared. 2.697. And then if I just slightly modify this, it's going to be over 0.15 squared. It's going to be 7 and 4. I'm getting 11.187. And now F12. I don't agree with this. F32 going this way. Positive goes to negative, right? Positive goes to negative. Positive goes to negative. This one should be F12. This one should be F32. I disagree, and I'll have to ask about that. So I'm just gonna do it my way. Frank Sinatra. I'm gonna have 2.697 minus 11.87. What this is gonna be is it's the E net. It's gonna be E1 plus E2, E3, and so on. I'm getting negative 8.5 coulomb. We coulomb per meter? Yep. Let's see if that's right. Got a feeling it's wrong. How is it? Oh, okay. Yep. I took the distance 1 to 3. It's 2 to 3. So it's 0.2 plus 0.1, so that's 0.35 squared. Okay. Simple as. .05. Now to take this number minus this number, I'm getting 0.64 coulombs per meter. And the answer is maybe on the next slide. Can you get me to the next slide? How do you go to the next slide? Scroll wheel don't work. Okay, yeah. And then theta equals 0. And we were wrong. Force is in newtons. All right, yep. No time to waste. Chapter 22, example number 1. It's going to be very difficult to solve this one, isn't it? Without it being obvious. Okay, so real mystery what the answer is going to be, isn't it? Oh boy. So a test charge of 3. So let's just say Q equals 3 microcoulombs, which is 3 times 10 to negative 6 coulomb. Is at point P where an external electric field is directed to the right. It has a magnitude, so four times 10 sixth. Test charge is replaced with another test charge of negative. What will happen to the external electric field at P? Positives go towards negatives, so yeah, it won't reverse its direction. Is it A? Could it possibly be A? Yeah. Chapter 23. Gauss law. Oh, it's not loading. Well, it's half loading. This is what I'm working with here. What an awesome website. I'm so thankful. I have them downloaded. That's add-ons. Where's the downloads thing? I'm gonna have to download them and then open them in my own browser. PowerPoint and Microsoft, you actually are incompetent and you suck. You've never been anything but a letdown. This is how slides should work, by the way. See how I just scrolled and it didn't crash? It didn't bug out. It's called slides. It's literally a slideshow. People make fun of things for like being a slideshow. They call things a slideshow when they're very weak because of, yeah, can't even run a slideshow. So what's that say? Huh? You multi-million-dollar company. Cube with a length 0.14 m. Area of a cube. Just gonna be over the face of a cube. It's Gaussian surface. It's gonna be A. Let's see. Be 1.4 squared. So that's the area of a face. And let's see. We know I mess with the screensaver settings on my secondary laptop right here. When plugged in, dim the display after 45 minutes. Turn off the display after an hour. The computer to sleep in 2 hours. That seems more reasonable. Why is it on power saver? Put it in. Okay, my computer apparently was in power saver mode this whole time. We're in chapter 23. Gauss's law. Everyone's saying E, it's not really asking, so it's just asking for the electric field E. Now I know I have more Gauss's law formulas than what they have. Chapter 23. I've got flux equals just EA. They just go straight to Gauss's law. They don't talk about nothing. Flux is EA cosine theta, and this one's asking, what is the flux? Yeah, and my formula sheet here doesn't mention flux. So that's a 1 point down for that formula sheet. Not that it's poorly made, just is missing an equation that I need right here. So flux, let's write the cool symbol, equals E A cosine theta. Okay. And it's asking the net flux through the surface, net charge, Q enclosed by the surface. Okay, they give us an equation for the E equals and E is what, the electric field? The electric field is 3y. Well, we'll figure that out later, I guess. So we have the area. We know what is the net flux? RA, the net flux through the surface. B, the net Q enclosed. Do we need the equation in part B for part A? Flux is EA cosine theta. I think we do. How else would we find E? Okay. 3y. And we know the y. We know the distance y from here to here is 1.4. So what we need to do now is top, left, right, top, left, right. Bottom and back. For some reason, the only face we don't do is the front face. I don't get, the back is 0. Maybe the front's also 0. So let's just do this. Top, bottom, left, and right. Well, cosine of 90 degrees. That's why it's cosine 90, but wouldn't the top also be cosine 90? Why the heck does the top have... That's assuming the flux is a dead straight line. Boy, that's interesting, isn't it? Hmm. This is going to be 3 times... Well, this has a distance from origin to the top, 1.4 times 1.4 squared. And cosine, this cosine 90, which would make the top 0. All right, top 0. Don't quite know if it should be. I don't think that's how they did it here. So let's do the left. So the left is going to be Maybe. Yeah. So it does say that the left has a height of 1.4. So 3 times 1.4 times 1.4 squared, and then we're gonna have 3 times 1.4 times 1.4 squared. I have a bad feeling that this is gonna be 0. Well, wait. What the heck's a yj? That blended right in with the parentheses. A yj? J hat? 3yj hat? This calls for... Okay, well, here's the thing. It's calling a right and a left. It's calling a right 1.4 and a left negative 1.4. I'm going to be real with you. If this is the origin and everything here is positive, and then everything here is negative, and we've got a line or a point here and a point here, right? They're calling this point 1.4 and this point negative 1.4. We know that this distance is 1.4, so get this. Are we measuring from the origin? In which case, this would be 0, that point would be 0, and this is 1.4. Or are we measuring the distance from the edge to the edge, making it the distance here from one end to the other? Is that the distance we use? Because it does not make sense to me that a point along the 0 x-axis, along 0, has a negative value. And not even like an actual, like it should be dead on over this way. It should be this far away from where it's at with a value of negative 1.4. It should be here. That should be where it's at. That's what I'm not getting. That's one thing that I'm not getting, by the way, out of multiple. I don't understand that. Okay, so I'm going to watch a video.
If you haven't done so yet, please pause the video and try to answer the question on your own or listening out. The first thing that we want to know about the diagram is that the situated horizontally, vertically. Just take note of the axis. And if we look in parts A and B, The electric field is acting exclusively as a j-hat component. And of course, that means that the electric field will be acting exclusively in the y direction. And so the total flux in the x direction is going to equal 0. Total flux in the z direction also going to. So we only have to concern ourselves with the direction. Now, we'll next note that
How did
in the x direction is going to equal 0. Total flux in the z direction also going to. So we only have to concern ourselves
okay.
with electric flux in the y direction. Now, we'll next note that because the cube has an edge length of 1.4 meters, that means that measured from the origin here to this surface right here would be a distance of 0.7. And similarly, measured from the origin to this here also be 0.7. And there are actually two.
When he says origin, he's drawing a line at the origin of x, y, and z. But he can't mean that since the cornerstone of the cube is on the origin x, y, and z. Meaning from the origin, as you can clearly see, it runs from the origin along this axis. And his center is the center of the cube, which should be here. Should be lower. Should be more like he's doing it along the x-axis. That's how far off from the x-axis it should be there. But maybe that's just him visually just lining things up that shouldn't be lined up. I did just want to note that. It's clearly not in the origin. It is origin of x, y, and z, but the origin of the cube. Goodness me. That's confusing me even further.
We're going to have to come up with two for the electric flux. The first surface that we want to consider will be drawn in the following way. It's somewhat difficult to draw and to visualize, but it's essentially the left face of the cube. And what we'll notice is that the left face of the cube has a y coordinate of negative 0.7. And we know it's negative 0.7 because we can arbitrarily assign this direction positive y here being negative. And so technically, that surface right there has a y axis. Now,
I disagree. Let me look at the face sits dead along 0 of the axis. There has to be either another reason. He's flabbering. He's waffling. It just does not make sense to me that it's sitting at 0 and he's calling it negative 0.7 as if it was that. And lastly, we never split it in half here. It gave us an edge length of 1.4 and we kept it freaking 1.4 the whole way. The whole way. So why is it in the same problem? Same exact problem. Why is his all of a sudden 0.7?
For this very same surface outline.
I want to know if he's blind or if I'm retarded.
And when we look at that surface, we want to make sure that we project the differential area vector perpendicular to that surface and pointing away from the interior of the cube. And again, we always want to draw a differential area vector perpendicular to the surface and pointing away from the interior of our cube. So in other words, if we were to draw a differential area vector in this direction, that's because it forms a perpendicular orange surface and it points away from the cube. Now we can express that differential area in unit vector notation the following way. Say that dA will equal dA multiplied by negative. And of course, the reason it's negative j hat is because it's pointing towards the negative. For that orange surface, we can finally turn to the expression for the electric flux, which asks us or tells us to take the entire integral around a closed surface in this case, square by 2. Integral product of field vector. And for the electric field, at least for parts A and B, we were given this expression right. So we can fill that in for the, and then we're multiplying it by that differential area vector. So that is. Now, when doing this dot product of a j hat and another j hat, those essentially will cancel each other. Now, let's not forget that the y coordinate of this surface is located at negative 0.7. We actually plug in negative 1. Of course, when we multiply that.
Okay, I'm a little mad at that, so. Also, why has Toper been down? I don't think I've gotten it to load in a good while. Flux equals E cross A. I like that. That's simple. It's super dead simple. They don't fluff nothing up. And they're getting the area of one side. Here's the thing. 3.96. 3.96. That's E. E cross A. E total A. That's through one face. But get this. First, which way is the flux going? You know what I mean? Positive and negative cancel, positive, negative cancel, and positive, negative cancel along all three faces couples of the cube. Net flux through the surface. Yeah, but flux left and right would cancel. Flux top and bottom would cancel, would they not? Toper's never gonna open. Should be never gonna oper. Yeah, I guess I'm just hung up on the left and right thing. I'm not gonna. I won't believe this is to the left of a line that I see that it isn't. I'm gonna write an email. If it's just a poorly drawn diagram, I'm gonna be pretty mad. Why do I have to sign in? I am signed in. And Microsoft made this Outlook thing, yeah. Did I paste an image or did I not? Come on. Let me control V. The diagram shows the left face along y plus Okay, guess rain check on this one. Very mad. Very mad at this question. (24). Example 1. It's just a huge waste of time. Actual huge waste of time. I could kill somebody. Come on, dude. Can you guys guess? Can you guys guess that it's glitching right out? And then I'm gonna have to click on file and then save it as a PDF. Can we all give Microsoft a large round of applause? Gonna kill somebody. Okay. So I can't believe it's been 45 minutes since I worked on that piece of garbage problem. So how long do I have left in this study session? 16 minutes. Time that doesn't add up. I don't care. Electric field in a region of space has components. That's weird. 4 nanocoulombs. X variable. A is put on the y-axis. Yeah. Wow, I can just say the distance overall is 3 meters. Point B is on the x-axis. 4 meters. What's the potential difference? This is a 3, 4, 5 right triangle. And chapter 24 we're asked what is delta V. Delta V is the change in U over Q, otherwise known as the change in work over Q. Work is FE D. FE pardon me, I'm trying to find FE. I don't think they noted in the formula sheet FE, but it should be. I might have just used it. FE equals QE, is that what it is? I'll see, let's see. FE equals QE. And then E equals surface over, well, we won't have that. KQ over R. KQ over R squared? Or I think it might be R squared. Yep. And that's we're not told if point A or point B. We do know that E along x-axis is 4 nanocoulombs. Or maybe they want us to plug this x into this. FE force of E, is that what they're trying to say? Or they just call it E dot D? Force vector of E? Maybe. So if that's true, let's try maybe it's Q E equals K for R. We don't know Q. E equals FA. So, problem solved. We need to find work. We need to find work. Let's Let's make this a different color. Let's make this a fun one. Yep, pink or pink. Yep, perfect. Okay, we need to find W. Find W, we need to find FE. Find FE, we need to find Q. But we needed a Q anyway. So how do we get Q? Q equals... There's a few things I guess Q equals. E equals QD. For an electric dipole moment, though. My screen went... I just did power save settings. Why did it just... I saw it go blank and I was just using it. Not blank, but dim. F equals QE. We can find E. We're not given F. We know E equals the potential E or potential V. E equals negative potential V. We can set E. No, there's too many unknowns. Wait, we can get the E equation. What we could say is delta V equals from initial to final E D. This is D L? D lowercase l? I think this is our best shot. So what we can try is this whole equation here, plug that in for E. The X, don't know. We're doing it over the EX, so why not? And its initial position is going to be 0x, and its final position is going to be 4x. Or is it talking about the length here? Because it would be 0 and then 5. So it's either 0, 4 or it's 0, 5. I'm not quite sure. Is it asking for the total length of the distance? Or is it asking for just along the x-axis? So now from there, it'll be 4 times 4. And plugging in x for x, the little x variable, times dl. Well, if it's initial final and we're doing d of the length, I guess it's going to be 5. We're going to multiply this by 5. And these are all constants, so they all go out, and we're left to integrate nothing from 0 to 5. Unless derivative of L, there's nothing to solve there. L's 5. Do I have to know derivative constant? I think it's going to be a constant, right? Or is it 0? I'm gonna look up this one now. Hmm. Maybe I was onto something. Dang it. On the wrong screen when I zoomed. Now it'll never snap back. It'll always look weird. It's too zoomed in, that's not zoomed enough. Okay. They're keeping X. And that's what they're differentiating about. And how would I know not to plug in X for X? You plug it in, and that's the wrong thing to do all of a sudden. So this is actually looking fine. It's be 4X and then DL. DX. Okay. And then this is just the X direction. 4, and this is 3. This is gonna be 4X. So there's no variable. Just call it 0. I want to know why exactly that became 0. And then this one is 16. Wait, no. This would be 4 squared over 2, which is 4, which is 4 times 4. Yeah, how does this work? 4x squared over 2. This becomes 2x squared. 2 times 4 squared. I'll just write it as 4 times 4 squared over 2. It's the same thing. I'm gonna make sure it's the same thing. Something just makes me think that would be fun. Why is it negative? It is negative, and I'm gonna go back into Windows power settings because it's still making my screen dim. I'm just keeping you open to look at my notes. I'm not gonna be touching this computer much, so please, power options, listen to what I said. Because I went from power saver, isn't it? Yeah, because after I just changed all the power saver settings. Goodness me. 10-minute break. Okay, yeah, let's get it now. Let's get it. Too legit. Quit. Get it. VB minus VA. So this is B. That's A. Negative 32 is VB minus VA, right? Because the other one's just 0. Volts. Pardon me. Someone was messaging me. Quickly replying, trying to help them out with a tech thing. Okay. So now we go back and we cycle to chapter 1. And I'm just going to download chapter 1 right now. Save me the trouble of trying to... It won't even let me do that! Dude, it's so slow. Okay, finally it loaded my... Scroll down, come on. I didn't click, that was all bugs, by the way. Okay. We did 21.1, let's do 21.2. Okay. Okay. Q1, Q2, Q3. -4 microcoulombs. Whoops. It's the same as the last time. 3 times 10 to the negative 6. And 4 times 10 to the negative 6. And then negative 7. 7 times 10 to the negative 6. And then we're gonna want F1, 2, and then F1, 3. I can move F1, 3 a little bit lower, F1, 3, and this is going to be equal to 8.99 times 10 to the 9th. It's going to be 8.99 times 10 to the 9th. And then Q13, Q12. This is going to be 3 times 10 negative 6, 3 times 10 to the negative 6 times 4 times 10 to the negative 6, and then 4 times 7 times 10 to the negative 6. This one's going to be 1, 2. This one's going to be 0.2 squared. This one's going to be 1, 3, which is 0.15. Now to type this in. Okay, I'm getting 2.697 and I'm getting 8.39. And now that's a negative, that's a positive, that's a negative. It's going to be going this way and it's going to be going that way. So for Q2, last problem, I can see why it was the other way around, maybe. But in this case, Q13 minus Q12, 8.39 minus 2.697. .7 newtons. Yep. Very happy. Chapter 22. Just download this as a PDF. Do I wait or do I click again? Oh. Oh. Ooh. I'm just going to click once. I'm going to leave it. All right, we're good? We're good. Save as. PDF. So snappy. Once it's downloaded, it's great because it's not running off Microsoft's garbage server. So I'm going to have to break this one down into 2 pictures, I'm pretty sure. So we're going to have this. And then we're going to have that. And I think, are we supposed to be given these? No. Okay. Okay. So we've got a point P. Length sides of 5. 5, 5, 5. You guys get the drill. So we have charge Q1, Q2, Q3, and Q4. This is chapter 22, which is a whole bunch of stuff. But this looks like it's a something like a point charge, they might call it. Don't know. Don't know. Wish I didn't care. So now we just have to figure out what this distance is. The fun thing is if we find it for one, we find it for all. So we know if P is in the center, and this is 1/2 A. So now our triangle is going to be big side of the triangle. Call it R. No. Let's call it big R. Is the square root of 5 squared plus 2.5 squared. Since this is side A, this is side B, and this is the hypotenuse, this is going to be C squared equals A squared plus B squared. But we're taking the square root, so we don't have to say it's C squared. We just say it's C. So this is going to be the distance from P to any point Q, which is very nice. 5 squared plus 2.5 squared. This is going to be 5.59 centimeters. Should have converted to meters earlier. This is going to be 0.0559 meters. Okay, we have R. It is little r. I lied. I tried to cheese it, church it up or whatever they call it, but no, it's little r. Chapter 22. Well, what's it asking? It's asking for E net. For one, we're not given any of the charges. I just realized that's bizarre. Is it even solvable? With no charges? I don't think it is. Here we go. We're gonna need those. Okay. 10 nanocoulomb, negative 20 nanocoulomb, 20 nanocoulomb, negative 10 nanocoulomb. 2, 4, don't cancel. 4, 3, don't cancel. 1, 3, nope. 2, 3, yes. 1, 4, yes. Okay. So Boy. So let's just do the E equation. E equals KQ over R squared. We have our R, we have K, we have Q. Okay, so we can just find E1, E2, E3, E4. Okay. I don't know how to get it to the center though. We're finding all of them. We add them all up and divide them because adding these two and dividing them gets us here, and adding these and dividing them gets us here. So maybe adding them all up and dividing them by 4. Or maybe because one's pulling the other one and the other's pulling the other one, each one's pulling themselves towards each other, it would end up in the center anyway if we just take the net. Well, who knows? E1, 8.99 times 10 to the 9th over 10 times squared. And since the only thing that's changing is here, we can just multiply it by 2 for these two, and then it would be the same for E4. Okay. Huh. Realize something. This is going to be 1/2 5, this length here. It's going to be 2.5 squared plus 2.5 squared. Which I don't like. I don't like that this is not the same as what the teacher got. But dispute this. We have a point here, and we're trying to find that distance, right? This height here is 1/2 A, and this length here is 1/2 a. 1/2 of 5 is 2.5. So the square root of all of that should be that. It just should be. And there's really nothing to dispute there. However, the teacher said it was 5 square root 2. Squared. So yeah, that makes sense. It also just makes sense. What she has is the distance q1 to q2. Which is just r squared. No, it would be r times 2, which is different than r squared. So the distance r is not what is it the distance to? Is it just the distance to the first to what it's attracted to? So you can't have a charge in a vacuum because the r would just be what it's closest attracted to. I was taking it to p, what we were trying to find. But really r there is the longest distance possible from q1 to anything. It could easily have been stopped by anything along the way. This is the furthest distance it can travel before being stopped. So is r the furthest possible distance something could be? Gosh. What's r? I have this test on Friday, mind you. I also don't like how you can't just drag something through a window. See how it gets stopped here indefinitely? Whoa! It didn't even know I had a stroke trying to think about just transferring cleanly from one screen to another. I see this one was slightly shorter, so I clicked that one, but this one's newer, so I'll click this one.
In part A of the question, we have 4 positive charges that are arranged at the corners of a square, and we have to figure out the magnitude of the electric field at that location, center of the square. We have marked the charges Q1, Q2, Q3, and Q4. And the first thing we want to do is draw in the 4 electric fields that are produced by each of the charges. For example, let's start with the charge Q1. What we do is we go to the location of interest, which again is the center of the square, and we place a positive mass charge. We ask ourselves, okay, if I put a positive test charge there, in what direction, either towards the positive charge or away from the positive charge, would that test charge be pushed? We all know that opposite charges repel one another. So this positive test charge would be repelled by the charge marked Q1 because Q1 itself is positive. Therefore, the electric field would point away from Q1. So we could label that field, and that would complete the direction for E1. The next thing we do is move over to Q2 and we repeat the process. We imagine that we place a test charge there. Else would it be pulled towards Q2 or pushed away from it? Well, Q2 is positive, so it would be pushed away from it. And therefore, the electric field E2 would be pointing in this direction. We continue on with Q3. I put a positive test charge in the middle, it's going to be repelled by Q3. The electric field will be pointing away from it. Finally, on Q4, same story, it will be repelled. We're going to direct an electric field vector away from Q4. Now, what is interesting in this case is that all of the charges are the same magnitude. That because the question says so. We also know that the distance from each charge to the center is the same for each of the four charges because they're located at the fourth. In what direction, either towards the charge or away from the top charge, would that test charge be?
Yeah, we don't have a positive charge though.
In order to determine the magnitude and direction of the resultant electric force on the chart that we're going to want to first draw a free body diagram of forces. It turns out that there are three electrical forces charges. Understand the notation that we have used for these electrical forces. You can go back to the diagram and notice that we have labeled the charge Q uppercase A. The charge down corner of the square is labeled uppercase B. Over here is uppercase C. So now these force notations would read as follows. This upward acting force would be the force that charge B exerts on A. If you'll notice that force is pointing up, and the reason for that is because charge A, which is positive, and charge B, which is also positive, would be repelled from one another. And so what that means is that charge B would be pushing charge A away from it in the positive y direction. And that is why we have labeled it up. In a similar manner, we've labeled the force acting to the right as A. That would be the force that D is exerting on A. And again, it's a repulsive force because they're both positively charged.
Q1's gonna be going not to Q3. Positive charge to the only other positive charge. It just doesn't quite make sense to me.
It is important to note that
in fact, Q1 would want to be going the dead opposite way.
Let's look back. We've arranged three forces along the left side of the table and the X and Y component. To the table over so that
Yep. Okay, I just don't get it. That's our R. All right, I'll just have to accept it. Okay. This is actually 0.07 squared. Ah, this is nanocoulomb times, also times 10 to the -9th. Okay. I'm getting 18,346. Way off. Five square root 2 is the same thing as I have. Am I off by 1? No. (8.99 times 10 to the 9th times 10 times 10 to the -9th. Okay, well, I'm seeing how they got it. So here's the thing. 0.05 divided by the square root of 2. Wait. 5 square root 2. Whoa, 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 whoa. Zero point zero 353. This is what I thought. Point P. Now get this. 5 square root 2 is equal to 2 times my R. Right? 0.05 square root 2 equals R. Maybe that made sense to you guys, but I think I was right this whole time. So my flaw in math is not knowing that 5 square root 2 and 0.05 square root 2 don't change the decimal place of r. They multiply it by 2. Multiply it by what? What would 0.5 be then? If 0.05 is multiplying r by 2. That's bizarre. I don't know how that works. Because point is 5 square root 2 is the same as 0.05 square root 2 times 2. You would think that 0.5 times 2 would be 0.10? No, 0.25? 0.25 square root 2 and 5 square root 2 would be half, right? No, it's not half. Oh, gosh. It's because square root has an exponent. It's raised to the 1/2, so it behaves exponentially. Gosh, dang, I'm so stupid. So yeah, no, this headache was for nothing. I was right on instinct. It was instinctually correct. Uh, I was right so long ago too. Whatever, it's 71, 920. I think. What did they? Getting that. Wait. Yeah. Yeah. It's the same number. It's the same number. Okay, so this one's gonna be if those two cancel, these two should cancel. Very worked up. And what, eNet? How would we do eNet? Add them all up, divide them by 4. Adding them all up is 0. 4 should be negative. Yeah, is it 0? Okay, well, I see what they're doing. So now, it's gonna be E1x and y components of E1, E2, E3, and E4, which is going to be minus and then E2 minus 2 times 7190 cosine minus 7190 sine 2 times 7190 sine 45. And then Q3 would be minus 2 times 7190 cosine 45 plus 2 times 7190 sine 45. It's gonna be 0. Right? Down left, down right. 2 downs and a left and right. Up left. Well, hold on. Q1. Make these all positive and negative. Okay. Positive, negative, negative, positive. So Q1 realistically wouldn't be going here anyway. It would be going away. It would be going up. Up and left. But you see, it's not calling it up and left in this. It's calling it down to the right. E2. It says E2 is moving away. I want to know why. Why is it that Q1 and Q3 are like charges and detract? That's not how like charges work, first off. And then Q2 and Q4, well, they're like charges and they see, there's attract, repel. They repel. It's the same thing mirrored, but they act differently. Q1 is headed towards the same sign as it. Q2 is heading away from the same sign as it. That's what I expect. X and Y. Why is it heading down? Let's just look at it. Let's see. From Q2, it's going left, negative X. And from Q4, it's going down, which is negative Y, X and Y. Positive goes towards negative, positive goes towards negative. Maybe that's it. Okay. So then Q2 in the Y direction. Haha. X direction, X and Y. So X, it's going to be going negative X. It's going to be going negative Y. Going positive y. I can't find a rhyme or a reason for it. It's almost as if it's just doing what it pleases. E2. E2 points at itself. Yeah, back to videos on this. But I don't know if I found a video that was... So Q1 is going down and to the right because to the right of it is negative and to down of it is negative. So it wants to head there. And then Q2 wants to head away from its attractive force. But I guess positive goes towards negative and negative doesn't seek out positive. So it's heading, it's getting repelled. I guess it's equally getting attracted by Q1 and 2, but getting repelled by Q4. Let's call it that. Just so we can check the constraints. And then Q3 wants to head away from Q1. No, it wants to head towards... it wants to head towards Q2. It wants to head towards Q4. Maybe we just look at... Well, let's see. It has Q1 repelling it, but it has Q1 and 2 in the X and Y direction attracting it. And then Q4 doesn't have that. Negatives aren't attracted. Positive goes towards negative always, not negative towards positive. I hope that's right information, but that's what I'm gathering. So, from that, let me work this. Q wants to go down and to the right. Q2 is not attracted, but it is repelled. So we've got E1, E2, Q3 wants to go up and to the left. E3, and then Q4 is just repelled. E4. I've made it work. It looks right. I have my own logic that I made myself, and it passed this run through. Which means that Q2 is positive here. Q3 is positive in the Y direction, negative in X. And then this one's going to be 7190 cosine, and then 4, it's going to be negative 7190 sine. So these cancel, and then all of that cancels. Wait. Negative and negative, they don't cancel. So this is going to be 4 times 2 times negative 7190 plus 4 times 7190. Wouldn't this whole thing just be 2 times 7190? Sine 45. Yeah, it is. So the answer I got is E net equals 10168.18. All right, the big takeaways is R is from the charge. Let me write this in hot pink. R is from the charge to the point you're trying to find. Okay, that's one. Two, opposites are seeking out negatives, but negatives are only being repelled and do not seek out positives. They are just repelled by other negatives. I want to make sure that that's correct. 2 hours, 2 hours, and timestamp. We just write this 2 hours, 1 minute into this. Okay, next problem. Here we go. A long straight wire. Oh, do I have anything to do with a long straight wire? Chapter 23, right? Gauss law. Maybe Gauss law is just Gauss law. So let's write down the one equation. Whoa. Almost makes me want to keep that color. Just do one fun. Yeah, let's have fun. We can have some fun, right? Gauss law. E dA, that's also a vector, equals Q enclosed over, is it just epsilon 0? Just epsilon 0. And this is a long straight wire. So you just imagine that is the long straight wire, even though it is neither, is enclosed by a coaxial. This thin-walled, non-conducting cylindrical shell has a radius 1.5 centimeters. Okay, so we're told R equals 1.5 centimeter, and you know what I could try? I've got a cheat sheet that I could use that's just all spheres and cylinders for Gauss's law, all of them that you might find. but let's try this. Try this. The shell is to have positive charge on the outside surface with a surface charge density that makes the net electric field 0. So we're also told E net has to be 0. We're asked what the cannon is. It looks like a cannon when I drew it, doesn't it? Yep. Area equals 2 pi r times L and E. I think E is always outside. And then is it boy. We got A. I'm not sure what to integrate this around. Let's see, the Q enclosed. The epsilon 0. And the Q enclosed for this just a thin walled, so it's just the outside surface. DL. You know? Yeah, I don't actually know how to start or finish this one. Gosh, dang.
Yo.
Dang.
Session number 10.
10-minute break. Maybe this one will be a slightly longer break.
2 minutes.
Alright, let's get back into it. That was like a 25-minute break. I apologize. Goodness me, it's almost 11. Might as well kill myself right now. Get it over with. Yeah. All this Gauss law nonsense, I'm just... Gotta find the cheat sheet or something. Maybe let's see. We've got... Lambda equals Q over A. We know A is that. We don't know Q. Q over... I see what they did here. This is going to be Q over 2 pi RL, but then recognize Q over L as lambda. This becomes lambda over 2 pi R. That's charge. Lambda linear charge density right here is 3.6 times 10 to the negative 6 C. So we can plug this in over 2 pi r, and this is going to equal charge the surface charge. Yeah. What's r? 1.5 centimeters, so 0.015. Okay, I'm getting 3.8 times 10 to the negative fifth. Okay. So the net electric field equals 0. Maybe we don't use this equation at all. Well, it's Gauss's law. Hold on, it's Gauss's law. It's got to come into play somewhere, right? No. Never does. Let me see the equations. Just shut my computer off that had the equations. Dang it. Did I have it written? There's no shot I had it written. Time to boot up Windows. It's funny, if I go to sleep right now, I get 6 hours of sleep. Done this every night. It's every night. Well, I'll just use this, so. E wire plus E shell equals 0. Wire lambda 2 pi epsilon 0 big R plus lambda 2 pi epsilon 0 lambda 1 big R equals 0. And this is negative, so actually this lambda equals the other lambda. Lambda equals lambda 1. That's too scribbly. But we have to find the surface charge density. Makes this 0. Lambda is Q over L, which equals 2 pi epsilon 0 surface charge, which means the surface charge equals Q over 2 pi epsilon 0 L. Q over L is lambda. Surface charge equals. Didn't we already write that? Lambda over 2 pi epsilon 0. 2 pi r? Whatever, epsilon 0. Big R. Which is 3.8 times 10 to the negative 6 all over 2 pi .015. I have no clue. I have actually no clue how we got here. Wait a second. This whole last bit we already found the surface charge. That was much easier than I made it. Still gonna star this. Okay. This looks like something that would be multiple choice on the exam. Three arrangements. 2 protons. Rank the arrangements according of net electric potential produced at point P. Electric potential. You know, I have a feeling about writing this one in like a cyan of some kind. Actually, we can rewrite this whole thing. That's gotta get smaller. I mean, that's large, but that might work. Okay, we got a formula. And E, we know E is a constant. So let's find E 4 pi epsilon 0 then. E is like 1.6. Let's see. 1.06 times 10 to the 22nd times 10 to the negative 22nd. Wait a second. it's a little bit cheesed out, but they're all D larger D, D larger D, D and larger D. So yeah, they would all be the same. Because you're going to plug the same numbers into this no matter what. It's a good equation to have, though. And this is going to have a lot of the problem in it. Not really. It's got a lot of the work I would normally do anyway in it. These. I can't erase it. It's that visual bug where there's a blue mark that you can't erase. Ah, it's annoying. Blue it is for this then. No. It's I don't know. I'm leaning. Would be there. Very bright. Very bright. I like it. We got all of our Q's. And we've got D. Calculate net electrostatic force. What is the equation for electrostatic force? Oh my gosh, that computer is a little bit slow. So, oh, it's Coulomb's law. Oh my gosh, yeah. Coulomb's law, chapter 21. So we just got to remember that F equals K Q1 Q2 all over R squared. Okay, so let's find F due to charge 2. Okay. Or of charge 2 due to other charges. We have 2, 1. F 2, 3. And F 2, 4. We're gonna have Q2 across all of them. This one's gonna be 15. Charge 1 is 6 times 10 to the negative 6. This one's gonna be 9.3 times 10 to the negative 6. And 4 is going to be 6.1 times 10 to the negative 6. Okay. Now, let's do F1 or F21, F23, and F24 equals, and then let's add them up. Because that's what E net is. E net equals the sum of E. I don't know, E sub n. Then what's R? Okay, that's what we're gonna have to find now. So we have force D equals 2.5 centimeters, which becomes 0.025 meters. Yeah. So R here, 2 to 1, is D, 0.025. 2 to 3 is D. This charge is square root 2 times 0.025. And it's squared for all of them. $12.94 plus 5. And that's going to be, well, let's see. I learned this from watching you. Q1, positive. Q2, negative. Q3, positive. Q4, positive. Okay. So the force of Q1, oh boy. Entirely. I don't think it would be entirely in the x direction. So let's call it 45, as if it was one here. Although it does look like it should be entirely in the x direction. Oh, it's a slightly different green. I kind of hate that. Hold on. I'm gonna do magic. Whoa. No, go back to the color picker. Got it. Okay. I'll just write on it like this. Oh, it looks bad. That looks bad. Q2. Perfectly repelled. No. Where was it going anyway? It's got no charge on it. Where's it going? This one, I know for sure is in this direction. And this one looks like it should just be completely X direction. I don't know if it's asking. We're gonna have to find it though. Well, Q is going everywhere. Q2, its charge is not getting attracted by anything. But I'm gonna call it that? Why not? I have to pick something. Something's better than nothing, right? Well, let's get on with it. It's going to be 9.3. So now I'm getting 2006.56. And for the last one, 6.1, I'm getting 1316.13. Okay, so we've got those three. Now, what I'm thinking is we break it into sine and cosine. For each of them, but wait. Hey, you know. That erases everything. I might have been onto something. They say it's all X and no Y. I have 3, 2, all Y and no X. And then this one's XY. 45 degrees. So if this is all X, then it's just going to be cosine. Wait. It would just be that many newtons I hat. They called all these F1 to F3 to F4 to. So I'll just have to make note when you're trying to find Q, the one you're looking for goes second, but it shouldn't matter, right? Shouldn't matter, right? So, negative, and then I'll just swap when I'm assuming everything is going to be. Q3 is now going to be X, Y, and this one's going to be X and Y. But it should also be negative. But they're calling 4-2 all positive. So if a positive charge going here is negative, but down here, it's going here, which can be broken up into here and here. And mind you, that's negative, and that's negative, but that's positive. Well, no, I lied. Force 2 going to Q1, negative. Force 2 going to Q3, negative. Force 2 going to Q2, positive and positive. Does that make it more clear that we're being inconsistent? Well, I'm going to watch a video on this and see if they put it in language that I can understand. I'm seeing is something that's very, very inconsistent. Really? This one also doesn't have any videos?
Good morning. I'd like to look over and do for you problem number 4 from another book on homework 18.2. Problem states there are 4 charges on a question. Or charge 1 on charge 4. I can calculate those, but I can only calculate them in terms of Q, K, and R, or in this case L. I can just
I like this. I like how he's drawing this.
before I do this vector I place it here. Because what I'm about to draw in green is the net force on or the blue and the red. Okay, so the green represents the sum, actually, the vector sum of the blue and the red. Square root of a squared plus b squared, because it's a right triangle. F on 4 equals a q over r squared. Of course, the q's are identical, and so I express this as kq squared. The distance r is L, call that L squared. Likewise, this is the same as F 3,4. Okay, so both the red vector and blue vector have this value right here. The green vector, of course, is equal to the square root of a squared plus b squared. Okay. We have taken care of 2, so get kq squared over.
Notice how that's positive and this is positive, and they're adding positives and positives. They're not subtracting. I don't get it. They're all positive.
In charge B, which is
These ones are all positive. Those were all positive. It's showing here F12, F32. Negative, negative. But then these two are positive. And it just freaks me out. Why? Why do those get to be positive? They're all positive up here. And then their signs flip and the signs flip. And then, oh, their signs don't flip. We're good again. $21.3. I've got a test in 2 days. Technically, I fall asleep in a few minutes, and then I've got tomorrow. So I've got a test the day after tomorrow, which is 2 days. I really only have one day. I don't know how to express that any further. I have tomorrow only to learn this stuff. It's 11:30. I'm gonna have to call it. 3 hours and 11 minutes of work. That's fine. I'm gonna get through these tomorrow, though. I'll see you then.